welcome everyone. And yeah, just quickly introduce myself in English. Benjamin Kemper, I'm a doctoral student at ETH Zurich and Anhalt University of Applied Sciences in Germany. Started last year in April and with the research on multi-material properties of robotically deposited bio-based materials. I'm here part of the Digital Building Technologies group in Zurich and of the Materialability Research group in Dessau. The research is supervised by Professor Dr. Benjamin Dillenburger from ETH Zurich and Professor Dr. Manuel Kretzer here from Anhalt University of Applied Sciences. There we go. I've graduated from TU Delft with a master's degree in hyperbody robotic building in 2018. Before that, I've earned a bachelor's degree in architecture at the Cologne University of Applied Sciences, experimenting with 3D printing, 7-axis robotic milling, cutting, and printing as well with a robot, 3-axis CNC milling, laser cutting, machine hacking, so to say, the whole exploration of the digital and digital field and digital fabrication field. Another research I'm doing since my graduation is also to investigate in a fully computer generated and manufactured house. Sorry, there we go. And which is focusing on the usability and sustainability. But today we will talk about basically robots and printing and stuff like that. So this lecture will give you an overview of robotics in architecture and design. Basic robotic knowledge will be discussed here, as well as the potential of hybrid applications and materializations. Over the past couple of decades, a paradigm shift in architecture towards non-standard, intelligent, and interactive architecture has emerged. As we are at the beginning of that age of digitalization, where computational logic has become integrated into the field of design and architecture, we need to clarify how and why the new techniques and technologies such as programmed architecture and robotic milling and printing are to be incorporated in that design and build process. This presentation examines the intersection between the physically built robotically augmented environments and robotically supported building processes. There's something, I don't know. Okay, design to production, assembly and operation chains are supported by robotic means. The computational design utilizing the cutting edge tools available today allows us to step beyond the limitations of traditional drafting and crafting. So more often than not, curricula for those apprenticing as architects and designers are based primarily on conservative design processes. So these processes have the benefit of being universally accepted, but are limited, however, in their intricacy as well as in their techniques to execute our vision as creatives. So I will quickly introduce a little bit of history or examples that are important for me. Then I go on with an overview of robots, move on to my master's project and the robotic printing resulting from that. Then we will talk a little bit about multi-material theory and then focus at last on plastics and how to replace them with bioplastics and how to implement the printing in that topic. And then, of course, we can have some discussion. So in the following, I would like to briefly show you a few historical examples that have influenced me, among other things. It's important to know that the next examples and theories link the presented research and give a historical background to the state of the art of digital planning and fabrication of today. So for instance, in 1882, which is quite some time ago, Antoni Gaudi began with the building of the Sagrada Familia in Barcelona. And the building is just hard to beat in terms of complexity and richness of detail. At that time, there was obviously no digital planning possible, but somehow, and also with the help of his own inventions and custom-made machines, Gaudi managed to plan and unfortunately just partly build the cathedral. Then in the 1960s, the avant-garde group Archigram was formed around the British architects Peter Cook, Warren Chalk, Ron Heron, Dennis Crompton, Michael Webb, and David Green. The Archigram movement embodies a utopian avant-garde architecture, whereby the neo-futuristic designs, they were exclusively of theoretical nature. So all these drawings and ideas, it was just, they didn't have the ability to make them real, make them physical. So everything stayed on paper, but still very interesting project. And I think they come back these days. Also in that time, we have Levi Woods, an American artist and architect. He's also these drawings are purely theoretical design approaches. And he dealt a lot with these abstract methods of linking two components or two matters, mostly in a parasitic way. On the right, you can see that example. So it's also an interesting approach how to combine two materials, two objects, two ideas as well. And then we have the Bauhaus, which is here in Dessau, where also the Materialability Research Group is based, and it's an important building for the modern art and architecture, and an important step. And I think it's representing the principle of the form follows function, and we can see that also in that building. So with the Bauhaus, the industrial mass production also found its way into architecture. And again, I think also cars are always a good reference to the stuff we're doing. So this is like a very early assembly line of Henry Ford producing a car. And but these inventions were needed to create these new products in a high quantity for the same or for even lower prices, and to work efficiently. So, but that's quite some time ago. So now they look like that, or at least a few years ago, I don't know, probably they changed. And this is a Hyundai factory, and each robot there, everything yellow basically, is assigned a certain task. For instance, some are for spot welding of certain body parts of the car, some I don't know, move the car, some place some glue for the windows. So all possible actions are probably done by these robots, and then they do these processes, repeat them for years, and then they are replaced probably, and go to another life, sometimes at universities. And so I think this is a good picture, because that's what most people think when we talk about robots or industrial robots. I mean, of course, there's this other robot image of a human robotic machine, but if we talk seriously about this topic, this is what we see, and also see often in research projects of universities. But they can do something more. So I don't know. I don't know if there is sound. It's quite important for that video. So I hope you could hear that. It's a making of video. At the end, you can see the real video. It's promotional video for Kuka and some musician. I think it's quite interesting because when we see these promotional videos, it's okay, they don't actually did that with a robot, but here they show, okay, they can actually, it can play a bass guitar, it can play the piano, and it's so. I think it's a little bit funny. They have more of these videos where robots play ping pong and so on, but they can do a lot more than just point weld for 5 years the same spot on the car. So these two robot examples show the current extremes of what industrial robots can be used for. And in the following, to understand it a little bit better, I would like to briefly explain how a robot in theory works. And so many more brands. I don't advertise now for that specific brand, but I'm just used to work with a Kuka robot. So there's a base, and we can actually compare the robot robotic arm, how we often say, with a human arm. So there's the base, let's say our body, where the arm is attached to, and there's the first axis. So a robot consists out of multiple axes. That's why it has its freedom to move in space. So the second part is the shoulder, where we also have the second axis, another rotation, another degree of rotation in there. I don't know if you can see my mouse. I don't know, maybe. So this is the arm then, with the third axis, allowing for the elbow to move in that direction. The elbow again has a rotation in this direction with axis 4. There's the forearm with axis 5, and the wrist with the axis 6. So in all these axes, moving or movement combined allows for a high degree of freedom to move in space. Then we have a flange that allows us to attach our end effector. That's what we call the tool that we attach to the wrist of a robot. So in this case, it's a spindle for milling, but it can be everything. So everything you can hold in your hand or attach with a few screws to something, you can attach to a robot. So it can be a printing device, it can be a spindle, as you see, it can be something for hot wire cutting of foam, it can be a screwdriver, or even a broom or a flamethrower. I don't know. It opens up for some creativity there. And okay, now we have this robot here, and we know, okay, it can move, and you already saw it, how elegant the movement is in the movie before, but that doesn't help us if we don't know how to tell it where it should go. So what it needs is a toolpath, and the toolpath is the line, so to say, where the spindle in this case moves along. We have the TCP here. It's a tool control point. It's actually a plane. So RGB XYZ plane, which is fixed to the end effector, and that we try then, or we map actually on our toolpath. So what we need in the toolpath is just a bunch of planes that tell us the position, it's a point, and the rotation of that tool, how it should come to our toolpath. I can show you here in that example. This example will come back later, so you might see then the correlation. So it's a stool, it's a chair, and what you see here is the digital representation just by planes on this for the robot. So it's a radial milling. Actually, you can see it here already in the cells. So we tried not to do like a linear removing because of the shape of the geometry and also different aspects. The radial removement of the material was important. So if we zoom in a little, you can see already the topology emerging just from the planes and the colors of the planes. And even if we go a little bit closer, you can see now the points where the tool should go and the TCP plane should map on these planes. And according to that, the program calculates, it's called inverse kinematic, how the axis of the robot here should move. So we don't tell each axis, for instance, axis 1 move 10 degree in that direction, axis 4 5 degree, and so on. It's all calculated so that the robot also does not hit itself. I think for the general understanding, that should be enough for the robot. So this is an example for pretty basic milling with a robot. I did that in Cologne in a carpentry. They have this huge robot, and so it's different strategies of removing material. You can see here certain roughing to remove the foam. It's EPS, and then in the second layer we finish the surface and create a nice surface on top of it. So you can see it now. It's also radial, but it's done with a different program. You can see in a bit. Here it is my workspace in Cologne. So on the left, I programmed the robot. On the right, it's working in the workshop, and I'm observing it with a webcam. This was for a project for Omega. It's called the Giant Speedmaster. It's in a museum in Zurich, in Switzerland, excuse me, and it's huge. It's the part you just saw in the workshop was probably this size here, and I think it's 10 meter in diameter, and it's walkable. You can go inside. There's an exhibition. We were just we didn't do anything for the design or for the finishing, or so we were just there to produce these parts, these huge parts, with the robot. And yeah, this is one example what you can do. There's another. It's not mine. It's from the AA in London. They have this huge campus offsite, and they decided to build a barn from trunks they could find in the forest there. So they analyzed these. So I think that's quite interesting. So they used material which is actually there, analyzed, scanned these, placed certain properties on top of it, measured all of these forks, and then combined them into a structure of a roof of this building. You can see some optimization, some arranging of these trunks. So it's a super interesting project. That's why I like to show that one. So when they finally got their position of each trunk, they added certain parts to cut out and to connect them together. So here you can see actually the two-path, the robot moving, the code on the side, and here the real example, how they did that. And so they remove only material where they need to remove it. The rest stays how it is. Takes quite a while. I think they need around 6 hours for each part to mill. but in the end, they can then combine it to a structure and use actual material which they found, which is there. So it's a better way, I think, than just using like huge blocks of EPS foam made from oil. It's a way more intelligent way to say, okay, we use these trees and combine it to a structure, and we just remove a few parts with the help of robots. And here you can see the final outcome. And then they place the roof on top of it, but it's not interesting. So this is another example by Tom Pawlowski. And so he said, well, if you can attach everything to a robot, why not a chainsaw? And with a very systematic and intelligent cuts, he creates these two stools out of one trunk. You can see him. He's also studied in Zurich. So there's one, and there's the negative part, and there's another one. So quite interesting approach. And the last example of robots in action is the Carrara project by Jelle Feringer. They cut marble with a bandsaw, and it's huge and effector, you can see here. I mean, also a huge robot, of course, but this gives us a little bit the idea what we can actually attach to the flange of a robot. And with that technology, also new forms can be created that would have been impossible, or so much work and needed skill. But this is just done with a robot. Super cool, I think. Yeah. Sorry, there's one more. This is branch technology, 3D printing with a robot, and they did this structure where they print in the air, and because they use this plastic and it cools off super fast, they can create this lightweight structures. So they also did a pavilion for the Design Miami. I think the structure is then painted later on, and they are also working on quite some more projects. Exactly. So this is like the overview of robotics in architecture and design. Now I just want to show you a little bit of my master thesis and how that developed actually. So this is, it's called the running out of gas in the fast lane. So in this hypothetical situation, offshore drilling rigs will need to be repurposed. And it addresses the dangerous consequences of climate change in the Netherlands. They are facing rising sea levels and the loss of livable land due to flooding. So on the one hand, we need to research possibilities to slow down the process and also change our way of life. And on the other hand, we must look for concepts and design proposals to support a lifestyle with radical climate changes. So how are we going to live in the future? Which role will architecture play? So you can see a unit, a living unit, I've called it. So it seems to me as a balancing act between a utopia and dystopia. And the project showcases the possibilities and benefits of a computational design on multiple layers. So the design is developed with the use of data gained through analytical methods. So agent-based modeling, for instance, differential growth systems, diffusion limit aggregation systems help to create this unconventional, however, logical schematic framework for this work. So on macro to microscale computational design strategies were then combined with material computational robotic manufacturing. You can see it here in the end. So this is also and effector I designed myself for silicon printing that we did then on this three-dimensional shapes of foam, of EPS foam. So after I've graduated, we took the project to SimAUD and did another workshop with a silicon printer there. And here you can see another iteration of the prototype of the printing and the multi-mode action of the robot. So first we created this this form, and with a milling, and then changed the tool to the silicon printer and placed the silicon where we wanted it to be in these pre-engraved curves. And then as another layer, we introduced also a certain wiggle to the two path of the silicon to create a linear one line layer of this print, but with these wiggles, they would overlap each other and create a wall thickness with just one line. And from that project, the hybrid chair derived, we can see also similar techniques, and it all comes together there in a way. So it's as I said, a follow-up project and derived from that robotic printing system. You can see the final result. It demonstrates the integration of multiple robotic production methods, so the hot wire cutting before here, the roughing, and it results in a novel multi-material system, symbiosis of hard and soft materials. The component of hard and soft is realized through developing and integrating of subtractive and manufacturing and robotic 3D printing. To mention some names, the hybrid chair was developed by Sina Mostafavi, Danny Fisher, and myself, which I all know from Delft, and it presents a customized computational design to robotic fabrication workflow of a material system composed of subtractively produced EPS and additively manufactured silicon. So what we did to achieve that design was to map the human body on this chair and try to determine where we need actually soft material, where we need hard material, where the body would attach to the chair. So we created this heat map, and from this heat map, the distribution of the silicon cells would result, and also the size. And at the same time, the inner shell, these cells needed to be sorted. So we developed a certain sorting algorithm for the robotic production later on. So there's also a multiple layers of radial sorting. So the radial sorting, and then the radial removement of the material of a cell, and then the radial printing of a cell again. So this is a scheme we've developed as well for this chair, and I think it kind of represents in a good way the structure of how we design. And so of course there's a red line in the middle, and it has a certain feedback and feed forward loops, and it influences each other. So we started with a design for a chair, and which at a certain point it was just modeled by hand, so to say. And then at a certain point of time we said, okay, that's good, but we want to shape the outer shell with a hot wire cutter because it's fast and easy, and can remove easy the foam with it. Then we did the shell analysis with the human body, created these cells, sorted these had certain iterations, the cells itself, all would then go at different stages to the robotic setup, how these two paths would be created, and so on. So this is kind of the where you can see that also how the digital drafting and the fabrication are closely linked together. Okay, so now we're at the multi-material. Also, this study or this research derives from the shown research, but it's more a theoretical nature, and it's here we did a few basic examples for the Digital Futures workshop in 2020, which is purely online because of COVID-19. So we designed these 4 hybrid prototypes, and they show 4 different possible topological integrations between 2 matters, red and white, or red and clear, and or A and B. And so we can see on the top left, we can see the idea of penetration of A in B. On the top right, we can see the gradient of A to B. On the lower left, we can see the distribution of B on A. And on the lower right, we can see the intertwine of A and B. So this is to be continued and will be later incorporated into my research of this bio-hybrid prints. In this workshop, then the participants were asked to design and prototype with this hybrid informed material systems. The goal was to address the symbiosis between the human body and the environment. So here you can see some digital files, the renders of certain designs of the groups with participants from all over the world. Quite challenging and interesting workshop, because the groups were formed. There was one in America, one in Asia, one in Europe, and it was hard to find an overlap of time zones, but they managed, and we were pretty happy with the results. And then we decided to print parts of these designs here. So the middle one is the top one here, and to have a physical representation of certain theory, how these 2 matters come together and combine a new idea. The last projects I showed were with the computational system and strategies to achieve these hybrid material systems. They were more or less all petrol-based, or at least hard to degrade, degradable materials. It's foam, silicon, plastic. It's not good. And I mean, we are all aware by now that these plastics, or the plastics in general, are a massive problem to our planet. That's why I focus on how to avoid them and how to create something different. And according to Samantha Staley, 100 million tons of plastic are consumed every year, which is quite a lot. And only 10% were recycled, which is basically nothing. And usually the plastic products end up in the oceans and pollute the environment. We know that, but it's also hard to avoid it, because they're so in our cycle of usage and everything. So yeah, Actually, I don't know. Here in Europe, we have this recycled chart. I don't know. Excuse me for my lack of knowledge there, but this shows the 6 big plastics or the types we can or could recycle. But the problem is, as I said, first of all, they need to be recycled, and then the right recycling method needs to be chosen. This is an issue, and the system does not really work in my eyes. So, but there are biodegradable polymers. There are, and there are 2 types actually: the agropolymers, which derive from biomass products, and such as polysaccharides or proteins, and the biopolyesters, which are produced from microorganisms, biotechnology, or fossil resources. You might know PLA, which is pretty famous for 3D printing filaments. It's always kind of said it's super biodegradable, but it's only under the perfect circumstances and time. So it's not the best material. And also a lot of these, even if they are recycled, do not dissolve for 100%, and the microplastics get back in the circle and harm us as human beings. So that's why I focus on the polysaccharides, mainly on starch. Starch is vegan, low in cost, and personally, I think it creates a promising bioplastic, so to say. The preparation is quite easy. You need a simple setup. This is an example with agar-agar and hemtau. So you basically just throw them all in one pot and mix them together, heat them on low heat, and stir until the biopolymer swells. And that's the process. It's a different one than from conventional plastic because it's a physical and not a chemical process. So there's no polymerization in a chemical perspective. We can use different ingredients to create this bioplastics. So we need a biopolymer, which is starch or agar-agar, as you saw already, xanthan gum, gelatin, sugarcane, stuff like that. We need a bioplasticizer, such as glycerol or sorbitol, and a solvent or biosolvent, water or vinegar. And then we can later on in this process add additives such as food waste, onions, banana peels, coffee grounds, or cellulose-based waste materials, hemp, for instance, or sawdust, paper. So the range for additives is quite large. There is already some work done. The Aguaoya project by the Mediated Matter group from MIT in 2018 that explores the 2D robotic chitosan and sodium alginate deposition. There's also the mycelium project by Klangbeck and Roos. They investigate in 3D printing mushroom-based objects. On the bottom right, you can see the bioplastic robotic materialization project here from Dessau, from the Materiality and DIA group, and that project kind of can be seen as a starting point here. And that's for me because they already did some prints, and my work is building on top of that. So this quickly an overview and some ideas. So the climate crisis has inspired the need to explore, as I said already, for alternative opportunities for sustainable fabrication processes. And plant-based bioplastic have emerged as potential part of a solution to quell the impact of the climate change. This research synthesizes cutting-edge fabrication tools, such as robotics and biodegradable materials together to create an eco-sensitive design that can support a realistic and optimistic human lifestyle for the future. So the possibility actually to do digitally program properties of an object is something that that is the interesting or the driver of my research. So it leads to a complex data stream that informs machines, tools, and the precise distribution of materials at the same time, which is quite interesting. So modifying these composition of recipes and merging different materials together allows for programming a range of varying characteristics in a single object. So for instance, these gradients between soft and hard, porous, solid, tensile, compressive, and we can incorporate them in the object and they will enhance the design and material space. So this is just to give you an impression. This is where I work here in Dessau. This is the lab, and on the right we can see the opening. So it's quite young research group here, led by Professor Dr. Manuel Kretzer. But we're growing, our team is growing, and this is with some students, we do experiments there when we're allowed to. And on the left, you can see a more recent picture of the lab. In November, we were allowed to conduct a workshop there with 4 students, all with masks and totally secure because the numbers were really low at that time. And that was nice because we could experiment and push the bioprints to a next level. And so the goal was to achieve a paste, let's say, a material for which is suitable for printing, for liquid printing, for a wet print, such as the silicon, which is also not heated up; it just dries or cures. And the challenge for the student and myself, of course, was how to the material should provide the right viscosity for the printing setup. I show you in a minute. It should dry fast enough to 3D print. It should not collapse on its own weight, and it should remain durable and tough after curing. Which is that's the tricky part actually there, and if possible, it should look appealing. Sometimes they do not, but that's how it is. So they were asked at first to do some manual testing with this pistols here, the silicon pistols and tools like that to try out if the material is printable at all, how it behaves after some time, how it looks like, and to test to get a preview of what to expect. And so they changed the ratios, of course, of the recipes, adding additives, and so for the better comparability and determination of the material behaviors, this layout was provided. And okay, they sometimes got a little bit creative, but still you can see a difference after some time. These are after 2 weeks, but I took the picture then, and the workshop was only 1 week, so we had to give some educated estimations about certain material characteristics, about shrinkage and molding. So we choose some promising mixtures to bring to this setup here. It's a WASP Delta printer. Also here in Dessau with this LDM, this liquid deposition modeling system that you would, or they use it for clay printing, for instance. And but it's quite simple. You have this tank where you fill in your material. You have a tube that goes to the nozzle. You add some high pressured air, and it pumps the material to the nozzle. There's a motor and a screw that gives a better distribution, and then presses it through the final nozzle. And that looks like that. Then it's a it's a time lapse. So the printing itself was the process of printing is actually really good, and the resolution is super precise. We can see some close-ups later on. So that was working actually quite nice. Here's the real speed of that print. Now I'm actually way faster, but back then I had to tweak a little bit the end effector and remove certain parts, so we have a higher flow of material. But also, it looks like it's just going, and you don't need to care, but all the time you need to sit next to it and watch it, observe it, and regulate the flow, the feed, and the speed of the printer. So here's some final LDM results after a short time, fresh from the oven, and after 2 weeks. So we can see actually that there is something happening, and this is more or less the point which is more struggling and also known for material scientists, that starch-based plastics, they tend to shrink a lot because the water wants to go out, and the material leftover stays, and there is a lot of forces going on, and if you place them in these forms, cracks will appear. And so it's a common issue, and it's also very common in general 3D printing, or in Zurich. It seems to be the common struggle. You can see some close-ups, some comparison, fresh versus after some time. Still the haptic of the result is super nice, I think, and very promising. However, the form is not how it should be, obviously. So this one is a little bit different. It's on eggshell and xanthan base. But it's just always the same. It's super strong. It's like cement, and could be interesting, but not really my focus. For me, the starch, as I said, is more interesting than the xanthan and eggshells. However, interesting and very promising result. Here's another crazy mixture. It's not molding. It's actually food color. We try to determine the height, how high we can print in one go. Not that high. I think to give you an idea, was around 25 to 30 centimeters around that edge, maybe a little less. I would have to look it up. And also here's some before and after. So this is really where I am right now. So the testing, the optimizing of these results, or optimizing might be the wrong word, but the finding the right way to handle the material, and there are more than just one opportunity or solution how to tackle this problem. There's, I don't know how much time I have left. I got like one more part, which is
yes, there is
like
no problem,
5 minutes.
if you have more time if you want.
Okay, cool. Then I would quickly show you a video. It's just a summary. So, but I don't know. It's just nice to show a video and give me like a 3 minutes break before I finish off with the last part. Okay. So I didn't show, of course, the problems we've just saw earlier, but still, of course, thinking and trying to solve it. So there are different approaches that I try to follow. So one is the additive itself. Also, the workshop in November was trying to tackle that problem. But I think I found a better ingredient and better way. The second strategy is to change the toolpath actually to a pattern that better behaves with the forces. The third strategy is to change starch and plasticizer, sorbitol glycerol, to a different starch, to a different glycerol. There are many different, and some glycerols, for instance, are more resin-like, and so I'm trying to get my hands on this material as well. And the last point is, and the most exciting, is to introduce the robot. I'm still waiting for it because of the pandemic. Everything got delayed and so on. So it's the robot here in Dessau is unfortunately not there yet, but it will come soon. So, and then introduce a custom-made extruder for printing these materials and changing material properties on demand. That's the long idea, but that's the strategy. So the last example or experiment I want to show you today is with the hemp fibers. Or I did some more testing and also introduced patterns, as I said, and hemp fibers. You can see them already here in very thin fibers in the fresh print. And I used 3 different batches, one without, just starch based bioplastic, one with 1% of hemp fibers, and one with around 3% of hemp fibers. This is the last one, is around 3%. You can see already denser amount. Top view did different tests. You can see them in a bit. Here we go. So the lower one is the control group, the middle one 1%, the top one 3%, and it's a time lapse. It will loop, so don't worry if you missed the beginning. You can watch out now. So there you could see already the difference. It shrinks immensely. However, you can see already in these 3 groups a difference of shrinkage. So I think it's a promising direction to introduce these hemp fibers or fibers in general. I just need to test how where's the limit of how much can I put in there. Here's some more close-ups of the dried or the cured result. Also of this one. So there was actually no cracking. It was just shrinkage, but less than with the middle one. However, there was no cracking, no destruction of the actual prototype. So this is quite promising. So I think all these parameters need to combine in one setup to actually create a working robotic printing setup with these bioplastics. Here's some more. You can see also forces going upwards in the Z direction. Less with more fibers, again proving that the idea is right there. And here fresh print versus cured prints, and I think here we can see exactly what I was talking about. It's try to match the scale here. So we can see, I think the pictures are talking for themselves. And yeah, that was about the last research experiments. So as an outlook, I already did that actually with the 5 directions or multiple directions, how to solve these issues of cracking and the forces in the material. I'm really happy now that I can actually, if we look back to where I started, which was super nice as well, but milling foam, I mean, this like was crazy back then. The whole workshop was as it was snowing for weeks, and the material is not good at all. So I'm really happy now that I'm actually can use my knowledge from robotics and digital programming and stuff like that to put it in this new plastics and biomaterials and create a new strategy there, which is as I said, I just started a year ago, and the material, I have no idea about chemistry or biology or whatever you need for that. Talking to experts, of course, but it's tricky. So that's also why I try, if it's somehow always possible, to do these workshops as last November, which was extremely helpful. And also looking for the robotic workshop in Quito whenever it's possible. And yeah, I think from my side, thank you for listening.